Welcome everyone. People are still filing in, but that's been 1 minute, so I think let's get this started. Um, I'm told to project to the back of the room. Can you all hear me? Are we good? We're a little quiet. Oh, is that better now? Okay, I'm so sorry about that. I would like to welcome everyone here. We've got a great crowd here in person, and I'm sure we have one out in virtual attendance land as well. This is the session on brain and the future of computing, emerging perspectives in embodied NeuroAI. Lots of exciting questions, and so I don't want to take too long, but you noticed if you were at the fireside chat last night with Director John Nye of the Brain Initiative, he brought up a question about how neuroscience can continue to inform AI, and brain should maybe have a role in that. And he announced that we're going to have a workshop later this year on the topic, and so I want to give you some more detailed information about that. We are looking at November 12th and 13th for a 2-day hybrid event. This will be the 2024 Brain Neuro AI Workshop. We have a great internal planning group here. You can see on the lower left, and we have an external planning committee, including Tony Zador, who's here today, as well as Blake Richards from Mila, and Doris Sal from Berkeley, and Brad Imany from Sandia National Lab. So we're gonna be bringing in perspectives from neuromorphic computing, cognitive constraints, and neuro AI, and all sorts of great diverse perspectives. And so if you're interested in more information, please go to the blog where you can put in your email. And as further announcements go out, you will receive information about how to register and find and follow updates. And so we are beginning the conversation today with this session. We have 4 great speakers, and we're really focused on kind of the core scientific questions. So if we look at, everyone is very familiar with the amazing, impressive capabilities that we're seeing in the technology space in AI, so we can begin to think about what are the shared underlying fundamental principles between brains and AI that can maybe drive both fields forward. Like, what is the convergence science here? And so we're here to begin asking these questions, kind of with an inflection towards embodiment and control. So what is the brain-body basis of intelligent behavior, and what is the role of embodiment, and how can AI and neuroscience best work together? So we've brought together, like I said, Tony Zador, who's going to be talking about how to bring insights from neuroscience into AI. We have Tony Zador from Cold Spring Harbor Lab. We have Henry Yin from Duke University, who will talk about kind of reconceptualizing how to bridge neural activity and behavior. We have Kim Stachenfeld from Google DeepMind and Columbia, who will be talking about deep learning methods for integrating artificial learning systems into physical simulations using graph neural network approaches, and Gina Adam from George Washington University, who will be talking about designs for neuromorphic computing hardware that are inspired by the brain, and how to translate those into biomedical applications. So we have a lot of perspectives coming together here. We'll have short talks and then a discussion at the end. And so with that, I will turn it over to our first speaker, Tony. Thank you.
Well, I want to thank you all for coming here and for making this this workshop possible. I think this is an incredibly exciting topic, and it's just the right time for it. So I'm going to be talking just a little bit to give an overview of what NeuroAI. That's not me, yes. What NeuroAI, how neuroscience and AI can interact and drive both fields forward. So as you're all aware, there have been tremendous achievements in the last decade or so in AI. I probably don't need to tell most of you about ChatGPT. I asked ChatGPT whether it would pass the Turing test, and it modestly said that it wasn't sure, but I think it's being modest. It's pretty clear at this point that it would pass the Turing test, which is if a normal person were in conversation with it, trying not necessarily to trip it up, but figuring out whether that's a human or an AI, it would actually go very far to succeeding for most people. At the same time, there have been other kinds of advances. This is one of the most dramatic for protein folding. This has been driving, opening up tremendous opportunities in research, and there are all sorts of other advances in AI, big data processing that have been enabled by recent advances. I think what a lot of people fail to appreciate is that where we are right now in AI is the result of a nearly century-long conversation between neuroscience and AI. I could give a whole, in fact, I have given a whole talk on the history of the interaction between AI and neuroscience. Here are some of the highlights. In fact, what many people might not know is that the very conception of the computer by von Neumann, the von Neumann architecture, was an attempt by John von Neumann to take what he thought about how the brain works and put it into machines. And we could go through a bunch of these highlights over the last 100 that led to the place where we are today. But somehow we've gotten so far advanced right now in the AI field that a lot of AI researchers think that that's it. There's nothing more to be learned by neuroscience. And I don't think that's right. I think we are not yet at the point where AI has crossed the finish line in terms of doing everything we'd want it to, and we are going to continue to get insights from neuroscience on that. So the way I think about it is that there's a virtuous circle where AI informs neuroscience and neuroscience informs AI. And then along the way, we can now sort of reap the benefits of some of those interactions. There are consumer products that everyone has access to. There are research products, AlphaFold, EMSFold, Deep Lab Cut that we are all using. But the fundamental circle driving that needs to continue. I am inspired by, in fact, early in my graduate career, I came upon the words of Richard Feynman, another physicist, who said, "What I cannot create, I do not understand." And the idea there is that we don't really understand how the brain works unless we can actually build it or model it properly. Now, where are we right now? If I said that modern AI probably passes the Turing test, so what's left? And a hint at what's left is given by Moravec's paradox, which I won't read in full here, but it's a beautiful quote. But the idea is basically that what animals do is hard, and cognition and reasoning, which is what a lot of systems like ChatGPT are good at, is the easy part. So this is sort of a depiction of the things that are on the way to being, if you like, solved, and then what I would consider to be the really open questions that will benefit from more input from neuroscience. So as I'm sure most of you know, modern AI systems can beat any human player in chess or Go or almost any other game. With ChatGPT, they're now linguistically fluent in every language on the planet. They're getting very good at doing math. They're not quite there yet. These are subjects that, although we value them very highly and see them as the pinnacle of intelligence, we think that they're the pinnacle because they are the things that are uniquely human or the things that we're especially good at. By contrast, we take for granted the things that all animals are good at: interacting with the world, planning, using a world model. Those actually are the areas where even modern AI systems struggle. And that's where I think there's a lot of room for input from neuroscience to AI. And so to sort of formulate that, to crystallize that thought, we have been thinking about, if you like, an embodied Turing test. So going beyond a Turing test where the goal is to see whether the system you're interacting with is human or machine just based on language. Rather, the idea would be to see whether we can build systems that can interact with the world as effectively as humans. And so these are inspirational examples for what that might look like. So what is NeuroAI? the fundamental guiding principle there is that neuroscience has been the inspiration for most advances in AI and will likely drive progress in neuroscience and AI. So I'm going to talk briefly about 3 areas that I think are particularly interesting in this and lead into the next few talks. The first is that it involves learning, how we learn. So of course, learning is central to modern AI systems, but they don't learn the same way that we do. And I mean that in a very fundamental way. Or a great deal of animal behavior is innate. A great deal of animal behavior is already encoded in the genome and is available to an animal when it's born. That's probably least true of humans, but if you think about, for example, termite mounds, termites don't learn how to build a mound from other termites. They just know how and collectively engage in action that leads to a mound. A horse, a colt, when it's born, can already stand. Beavers have intrinsic motivation to build a dam. They receive guidance and training from their parents, but fundamentally they want to build dams, and that's built in. And we all benefit, all animals benefit from having a great deal of knowledge already present at the time they're born. So the second is, and I think we're going to cover this later, so I won't belabor it, using less energy. Modern systems, AI systems, use tremendously more energy. And here's just one quick fact to keep in mind. It took about 50 gigawatt hours to train GPT-4. That's about as much energy as it takes to power a medium-sized city like San Francisco for a week. By contrast, it doesn't take quite that much to train your child how to speak. And we know, roughly speaking, at the biological level, a lot of why biological neural circuits are so energy efficient, but we don't know how to transfer that to artificial systems. And finally, I'll end with the alignment problem. So this was nicely encapsulated by a quote from Nick Bostrom, who says, suppose we have an AI whose only goal is to make as many paper clips as possible. The AI will realize quickly that it would be much better if there were no humans, because humans might decide to switch it off. Also, human bodies contain a lot of atoms that could be used. So the future that the AI would be trying to gear toward would be one in which there are a lot of paper clips, but no humans. Humans, by contrast, would be less likely to make that particular error. Humans, along with all animals, know how to balance multiple goals simultaneously. And that enters into the greater ability of biological systems to engage in planning. So, with that, I'll just hand it over to Henry while you ponder the summary. Thank you.
Okay, so let me just start by showing some data. So these are single unit data collected in my lab. They come from multiple brain areas, mostly in the basal ganglia. And I'm not going to describe the details. I just want you to focus on the main pattern here. As you can see, there's a simple monotonic relationship between neuroactivity on one axis and some behavioral measure on the other axis. Okay, so this pattern is surprising to many because traditionally it's commonly assumed that the relationship between neuroactivity and behavior is more complex. So what's different here? I think the trick here is that the behavioral measures that we used are continuous. So we're measuring continuous behavioral variables like velocity and position, and we're looking at the relationship between single unit activity and the behavior. Now, in conventional approaches, when you look at this kind of relationship, you would arbitrarily create some events, task-related events, and then take the timestamps. So then you would plot the neuroactivity around these events in peri-event histograms. But in our approach, we assume that the behavior is a continuous process. So we will simply record behavior and neuroactivity at the same time and look at the relationship directly. Okay, so in the traditional approach, the continuity of behavior is simply ignored. The implicit assumption is that in between events, nothing is really going on. Now, using this kind of continuous process-based approach, here are just some examples of the kind of data that we collected. You can see on the left, we have activity from the basal ganglia output neurons in the substantia nigra pars reticulata. And in these neurons, we have a continuous representation of the instantaneous position of the animal. And these are X and Y position coordinates. And on the trial by trial basis, this relationship is always present. And the relationship between the firing rate and the behavioral measure is linear. On the right, we have an example from the ventral tegmental area, the GABAergic output neurons. Again, these neurons appear to represent pitch, yaw, and roll rotational kinematics, and the relationship, once again, is very simple. Now, just to summarize these results, we have found that the basal ganglia output neurons can represent kinematic variables very precisely. Not only do they represent these variables, they can also lead slightly the actual behavioral measures. So that's suggesting that these neurons can play a causal role in generating the behavior, and we confirm that with optogenetic manipulations. So if we stimulate or inhibit these neurons, we can produce reliable effects on the kinematics. So the first implication of these results is that the kind of signals that we recorded from the brain are analog signals. Okay, so there's an analog representation of kinematics, and these circuits, at least the circuits in the basal ganglia, are performing conventional analog computations. So these include operations like addition, subtraction, differentiation, integration. And the second implication is that in order to explain the kind of results that we have, in which the internal neural signals slightly lead and also cause the kind of behavioral features that we can measure, we have developed a hierarchical control model. And the control problem can be defined as in order to behave in the physical environment, you can't just repeat outputs because there are always unexpected disturbances. So repeating outputs doesn't work. What you have to do is to generate variable outputs each time to counter these disturbances in the environment. Okay, so in this model, we have a hierarchy of control systems in which the higher system dictates the reference states of lower levels. And so these act as descending commands, which are the kind of signals that we measured. They can specify the desired future state of the animal. And so we've implemented this following Feynman's quote. So we've built a robot that's capable of natural locomotion. And so this robot is a 4-level control hierarchy. Each level is a simple negative feedback controller, and it is capable of walking around in a natural environment without any training, without computing inverse kinematics or dynamics. in other words, without performing any sophisticated computation. The effectors used are also very cheap. So the total cost is less than $3,000. And also, I should add that there's no degree of freedom problem, so that each degree of freedom is simply handled by a dedicated controller. Interestingly, within this robot, we can also look at the signals. And the signals within the robot highly resemble the kind of signals that we recorded. Okay, so as you can see, basically what happens in this robot is at each level, the reference signals dictate the perceptual signals for the level below. And what happens is that the reference signals are quickly matched by the perceptual signals. And that's how you generate flexible behavior. So just to summarize, I think the first implication for embodied AI is that the relationship between neuroactivity and behavior is simple if the correct behavioral measures are taken. The brain uses analog computing, analog signaling in the control hierarchy, and that means it does not have to do these conventional forward computations or inverse computations. And therefore, of course, it's highly energy efficient. Current AI relies on symbolic manipulations. Can't really behave in the real world because behavior involves solving the control problem. That is, it has to use a control hierarchy to generate variable outputs and achieve consistent results. And that's all I have to say. I'd like to acknowledge my lab members who did all the work and support by the NIH.
Hi, everyone. I'm Kim Stachenfeld. I'm a research scientist at DeepMind, and I'm also affiliate faculty at Columbia at the Center for Theoretical Neuroscience. Today, I'm going to talk about some machine learning work using deep learning for physical simulation, and I'll also talk a little bit about the approach we use for this, which relies on graph neural networks. So to start off, our kind of high-level motivation here is that we are inspired by these really complicated machines that are composed of multiple different parts, which each have some specialized function and combine together to do something greater than the sum of their parts. So here, this is an illustration, a schematic of an espresso machine that's decomposed into isolated parts so you can see what each one does. And those parts are not super simple, but they're certainly a lot more comprehensible than the entire object put together. And when we think about how humans solve problems at more of an anecdotal level, at a high abstract level, rather than looking, exactly at psychology data to be inspired by this, a big part of this is that we break down problems into comprehensible parts. And even though we're thinking about this for the inspiration of this project at a high level, a lot of folks who work in this area that I'll talk about are really inspired by the psychology of intuitive physics and how humans reason about physical problems as component parts that work together to produce dynamics. So the application we have here is that we're going to use neural networks to try and predict what's going to happen in some scene. So our approach is we take some data, information about physical dynamics, and we train a neural network just to predict what's going to happen in one time step. So here we have the state of the system at time t and the state of the system at time t+1. Our neural network's job is just to predict that difference, how the state of the system will evolve. This has numerous applications. One is efficiency. If we use a classical simulator, it is implementing the actual physics. And if we try to introduce approximations, those physics break down and it's sometimes unclear what to do. But if we train a model to just approximate what would happen at a lower level of resolution, that often works. And that's something we usually apply. These models are also naturally differentiable. This basically means that they support efficient optimization. And that's the key property that we're going to leverage here in order to use these models to design solutions to physical problems. And I think most excitingly for me, and also this has a lot of application to how we might use these models for neuroscience and biology in general, is that they can learn arbitrary or unknown physics from data. In the simulations I'll talk about, we're using neural networks to learn dynamical models from some simulator. We have a simulator, we're using it to generate data, we train the model to imitate that. But you can apply this approach to real data too when you don't know those underlying rules, and that's something that's really powerful. So the basic architecture of these models that is a really good fit for physics problems is that they use this graph structure to neural network. Particle in the scene, like a fluid particle or a vertex of some mesh that's in the scene. And the way the state of the system is updated is that each node gets a summary from its neighbors that's processed by a neural network. And we use the same neural network on every neighborhood, which means that we're basically learning a local model of how particles interact with each other. The same neural network is applied everywhere in the scene and just learns a model of how a neighborhood will change based on possible collisions and possible interactions that can happen in this small neighborhood that it's reasoning about. Just for context, this is similar to a more familiar form of model called convolutional neural networks, which are really common for image processing. Convolutional neural networks learn about local patches of an image, and you apply the same processing to each patch of an image and use that to process a scene. That way, if you have an eye detector, it's an eye detector anywhere in the scene. Here, we're applying a similar property, but for graphs. Another architecture you may have heard a lot about are transformers. Transformers have a really similar structure where each node or token is updated as a product of other tokens. But here, instead of limiting things to a small neighborhood, a local view, all nodes can interact with each other. And this local view is a really good assumption to build in a kind of baked in inductive bias that's really useful for physics. If you're thinking, hey, I thought transformers were for sequences and language modeling, usually the form they're represented is like this. Here we have the nodes arranged in a sequence, and the task is the prediction of the next node. So each of those little nodes might correspond to words in a sentence if you're GPT. The reason these local models are really important is because it allows us to learn a model that generalizes. And it generalizes in a really specific way. It'll generalize when you have the same local rules, the same local dynamics, but you arrange them into a different global configuration. So in this inset panel, you can see an example of our training data. It's a lot simpler than the domain that we can ultimately apply this to. It just consists of cubes of fluid falling onto ramps. But the reason it can generalize to this much larger and more complex scene with more articulated and complicated panels is because this is a different global arrangement of the same local rules. So this challenge that deep learning often has of generalizing to new problems that it's never seen before is kind of resolved because we've broken this large problem into parts that the model has seen, into local dynamics that themselves are represented in the training data. This approach is also really flexible because we're using neural networks and neural networks are expressive. We can learn lots of different types of dynamics. This is work that's some of which is done by myself, some of which others that I work with at DeepMind on different types, on different types of dynamical systems that we can model with this approach. So here what we were interested in doing, the project I'll talk about now, is seeing can we use this approach not just to simulate and predict what will happen, but actually to design things that intervene on the scene, objects that cause the dynamics to unfold in some way, which is really representative of this problem of design. Can we make objects that interact with the world and make something happen? So our general approach is we're going to break the problem into parts as shown. and use this to simulate what is going to happen. This whole process functions as a predictive model. We always apply, improve the design, see what's going to happen, and update the design to make it better. This ability to generalize out of distribution is really especially important for these kind of problems because the optimal design is probably not something we've ever seen before. If so, it would be a really easy design problem. So first, what we see is that we can use this to solve different kinds of problems in 2D. Here's a couple different fluid problems we were especially interested in. We see that using gradients through the model, leveraging the fact that these models are differentiable, is something that's really useful, and the models are better. Where this approach really shines is in super high dimensional problems, where we have a complex surface with many dimensions that we want to optimize. And I'll just briefly mention that the fact that we've broken the problem into parts, we can confirm that this really helps. If we look at solutions that don't take this approach, it tends to overestimate the quality of bad designs and underestimate the quality of good ones because they're out of distribution. You can see those blue and orange dots are out of distribution and therefore not falling along that diagonal line as they should. I want to just close by mentioning a few opportunities to apply this approach to neuroscience that I'm excited about. One is perhaps kind of straightforwardly connectomics and circuit neuroscience. These models are good when you want to learn how to relate structure to function, how you want to relate the structure of a model to some predictive dynamics, and reasoning about how counterfactual manipulations might change that. They're also useful for predicting biological dynamics, potentially like development in biomechanics. Neural dynamics also falls within this scope, particularly if you want to know how an intervention on your circuit might result in different kinds of dynamics. And then finally, at the more cognitive level, I research hippocampus and memory too, and thinking about how the brain might apply this relational reasoning, I think is its own really interesting problem that this could be applicable to. So I want to close by thanking my collaborators, and thanks very much for inviting me here.
Hi, everybody. Good morning. My name is Gina Adam. I'm an assistant professor in the Electrical and Computer Engineering Department at George Washington University. I want to thank the organizers for this wonderful opportunity and fellow panelists, very insightful talks. As an electrical engineer, I am particularly interested in the engineering constraints that we have to apply to systems. So to wrap up the presentation part of this panel, I'm going to talk a little bit about two key constraints that I think are very important for the embodied AI. In current AI frameworks, we have these large-scale models that we've been talking about, trained on very large server farms, right? We have these massive systems that consume a lot of energy. And these are because our algorithms are resource oblivious. But when we move to physical AI frameworks, we have to take into consideration optimization for physical constraints. And I want to point out two key physical constraints in the interest of time that I think are particularly important. Energy was, of course, discussed. For example, the latest NVIDIA GPUs that are used to train these very large-scale models are expected to consume in total more than the energy of small countries. So this becomes a very, very massive problem as we want to scale these systems even further because we need the hardware and the energy to support these large-scale algorithms. But another key constraint that I want to mention related to this as well is non-idealities, because AI models have shown to be powerful, but they can be very brittle to noise. And this noise can be external input noise, as you can see here, by adding just a little bit of noise that's imperceptible to a human. This panda image is misclassified as belonging to the monkey class. So that's no good. But one other thing that I want to point out is the internal weight noise. And as we think about new types of hardware, we can have these non-idealities in the hardware itself. And this is the work that my group has been working on. And we see that when we have these non-ideal hardware, we get a performance drop that can be in the order of dozens of percentage points because we have variability in the weight updates. So how can we tackle these problems? Well, in terms of energy efficiency, we already talked a little bit about analog systems and being able to have analog systems that can perform similarly to biological networks, as well as having the energy efficiency far superior than their current digital counterparts. But I want to point out that there is a problem that we're facing with analog circuits, and that's the fact that they are quite sensitive to variations. So our second key physical constraint, which is non-idealities, is going to be a challenge. And I wanted to point out here a work by a group in University of Michigan doing an all analog hardware accelerator for a convolutional neural network. And you can see here really good performance in terms of energy, but the performance accuracy is significantly lower than the digital counterpart for the software, and that's because we have these circuit noise and the precision limitations. So that's why I have become very interested in how we can draw inspiration from the brains in order to design energy efficient and robust hardware for next generation AI frameworks. And we see that biological brains are extremely energy efficient despite the fact that they have to deal with different variabilities. They are showing robustness to external variability, as shown here by increased brain size in terms of adaptation to climate change. And also robustness to internal variability. As an electrical engineer, it was surprising to me to learn about the variability in synaptic plasticity that exists in the brain. So the brain can perform robust and efficient computation with imperfect hardware. So how can we match that? Can you still hear me? Okay. So our grand challenge is to build these sort of artificial neural networks that can achieve the efficiency and complexity of their biological counterparts in these constrained environments. But the question is, what features of brain organization do we need to map to develop these neuro-inspired learning systems? As part of a project that is generously funded by the Department of Energy, and in collaboration with my collaborators from George Mason University, we're looking at drawing inspiration from the hippocampus because it is a key brain region for learning and the formation of memories. And we're looking to draw inspiration and build biologically realistic neural networks that can require us to have the same neuronal types that are present in that subregion of the hippocampus. And we are looking right now at the CA3 model. We also have the poster 206 talking in details about this. Our goal is to build small-scale variants based on the different types of neurons that are present in the CA3 and perform learning into these models. So I'll show just a few results on this. We're looking at the impact of excitatory versus inhibitory balance in these networks. And we see that the best networks perform in terms of accuracy at low initial spiking rates. So that's good news in terms of efficiency. We also notice that the networks that have excitatory to inhibitory ratios around 80 to 20% are performing the best by comparison with networks that are purely excitatory. One thing that we're particularly interested in is this neural diversity, and we're looking at drawing inspiration from the brain and embedding this diversity into our networks. And we see that actually networks that have a diversity of neurons, for example, pyramidal axonics, shown here with purple, actually perform several, like 10% or more better than the same type of neuron on the same task that has only pure pyramidal neurons. We are also looking to taking these insights and translating them into actual hardware. We are building different types of neurons into analog circuitry with different types of spiking behavior. As you can see here, we are also looking at having networks of these chiplets interconnected and building new types of neurons based on emerging hardware devices that show different types of spiking plasticities. And you can see here also, unfortunately, variability that we have to account for. With this, I want to summarize that embodied AI will have to take into consideration these two key physical constraints: energy efficiency and robustness. And analog AI can provide better energy efficiency, but we have to have these trade-offs due to non-idealities. Neuroscience inspiration and biological neural networks can guide us into building these new types of hardware translation, and we're looking to take these emerging hardware into new types of constrained environments like neurotech and implantable devices. With this, I want to thank the students and my collaborator, and of course, Department of Energy for the funding. Thank you all.
Thank you all for the great talks. A lot to think about, particularly interdisciplinary approaches. And so I kind of want to get right into the questions, given the time that we have allotted for that. Or a large obstacle in the particular kinds of interdisciplinary approaches that you see contributing to NeuroAI research?
Can you all hear me? Yes. Yeah, maybe I'll start with that one. So I think that for NeuroAI to move forward, we need a community of people who are bilingual in both knowledge of neuroscience and knowledge of AI. And both of those are pretty deep fields that require a lot of expertise. And the question is how to get that. And I'll say that we have a pilot program at Cold Spring Harbor where what we do is we take students and postdocs and fellows who have a background in AI and then train them up, embed them in neuroscience labs and train them up in neuroscience with the thinking that at this point there's a great deal of very specialized technical expertise in AI that's required to move through that field. We're also booting up a graduate program that is going to train people to be bilingual in those two fields. And I think that that's going to be kind of key to having the sort of rejoining of these two fields that used to be one. Any other thoughts on that?
Oh, thank you. I can largely just second that. I mean, I did my PhD in neuroscience and then went to DeepMind, and there was a real learning curve to getting oriented with AI methods and training neural networks and a lot of the engineering skills involved in that. So I think the more that's part of a curriculum, probably the better for uniting fields, and the more people aren't just like inventing it on their own, the easier that would be.
Gina?
Yes, I second that as well. And I also want to add that data is really important, and having access to data that we can understand as engineers from the outside neuroscience is very important. So thank you for all of the efforts that support gathering neuroscience experimental data in data sets that are accessible, and open source projects, open initiatives are really great.
Do we have any questions from the audience?
Thanks, everyone, for great talks. I'm curious, what do you think about the future of neuroscience and AI with quantum computing?
Maybe I'll take a crack at that. I guess as far as I can tell, there isn't really anything concrete enough in quantum computing to really have that be part of the mix at this point. I think that remains sort of at the frontier. It's, on paper, tremendously exciting, but I think it might remain a little bit like fusion, which has been 10 to 20 years away for the last 50 years. But who knows, right? Like at some point there may well be a breakthrough, and that will be transformative. But at this point, there are very concrete sort of opportunities for combining technologies that already work, or areas that already work, neuroscience and AI, and at least for me, that's what I'm focusing on right now.
Yeah, great session, and thank you all. So I have a specific question over here.
Gina had an answer.
Yeah,
I'm sorry.
I just want to point out, I'm working on neuro-inspired computing hardware, on neuromorphic computing. I'm a firm believer in it. And I think it's also because we have actual brains that do what we want them to do. So these key constraints like energy and non-idealities, we know that nature has found ways to solve around them. Quantum computing requires having like very low temperatures for these systems, for the hardware that they operate. And I think that's a major limitation. And so for that, you require energy, a lot of energy. And also there's a lot of sensitivity to variations in like the qubits. I'm not a specialist in that, but we don't have a counterpart in nature to like a quantum computer, whereas we have the brains that we want to emulate for neuromorphic hardware.
Great, thank you. And now to the audience.
Apologies. So I have a specific question to Kimberly. I learned that you are a martial artist for many years, and so how do you comment? Like, you must have a very strong like physical simulation model in your head analyzing your opponents. So how do you think your models compare with the model? Also, your models. And okay, the real question. So, so I study human language at the single neuron spiking level, and so we know that in patients like HM, and without this bilateral hippocampal system, and they can no longer learn, but they can still have seemingly normal conversations. So so then the specific question is like, what like subsystems in the brain might be carrying that out, and also relating to the your talk today, like how do you think the different architectures and models in AI map onto different systems, or the same system but actually kind of generalize across different artificial models, and like Tolman Eichenbaum machine variations of it for language, but is it really for language enough? Yeah.
I think the I guess the first thing that comes to mind, because that just hits on a lot of like different and interesting problems that are at the heart of like the open problems in AI right now. As it relates to HM and memory, I think one class of approaches that hippocampal research and our ideas about how hippocampus is contributing to cognition, but also language specifically, are RAG models, or retrieval augmented generative models. As you mentioned, HM was perhaps surprisingly, perhaps not surprisingly, depending on who you talk to, pretty good at just having a normal conversation. Like, it turns out maybe you don't need an abundance of episodic memory for that. Similarly, if you have a generative model that has that doesn't even have an enormous context or an external memory buffer, it can do pretty passively unless you're poking it and really trying to probe it on something extremely factual or something more complex. And the retrieval augmented generative models, what their approach is that you have an external memory buffer that you can access and load things into context in order to condition your responses and try to really like bias them towards specific retrieved information, almost like episodic information that you might have in your buffer. I think this approach is really cool because it's a nice way to take a large pre-trained model and then augment it with some specialized knowledge or factual knowledge or updated knowledge. And it's also really not much of a stretch to equate this with how we think about different memory systems working together in the brain. There's other approaches to how one might use long-term memory and how one might reference different memories. Maybe just get the biggest, get a really long context and throw everything into your context and just, reference that. But I think these retrieval augmented approaches, they're very lightweight. They're a lot more efficient, and they have real correspondence, I think, with how we think about memory in the brain. They're not a language specific approach. Right now a lot of research is just in LLM land, and they're often applied to LLMs, and specifically in the context of biasing language outputs to taking the more general purpose generator and then conditioning it towards something more specifically factual, maybe by referencing Wikipedia or recent news articles or something. So, but the approach itself is just kind of like, can you retrieve something that seems relevant to your current prompt? It's not domain specific, just the applications that are popular right now are.
Can't hear you.
No, we can't hear you.
This is a question from the online audience. What are algorithmic sources of robustness, e.g. error correction from the brain, that we could draw from?
So I think that's an interesting question. The way it's formulated suggests that that you have some algorithm that requires a very low noise regime to operate in, and then there are error corrections there. And I'm not really convinced that that's quite right. As Gina referred to, the brain is just operating in this wildly noisy regime. So central synapses will fail to release transmitter, will fail to propagate an action potential the 90+% of the time, right? That's not a regime where you want to keep correcting in the sort of conventional sense. So I think one of the real challenges is how do you compute in a regime where messages are transmitted rarely and sparsely, as in the cortex, and also highly stochastically. At least that's how I've been approaching it, maybe.
So that's why we're looking at the neuronal diversity. It's something that we think, to me, when I learned that there are so many neuronal types as an electrical engineer, my first question was like, why? Why do we need so many neuronal types in the subregion, and why there is so much diversity from subregion to subregion? So if I need to implement a neuromorphic chip with all of these neural types, I can do it, right? I want to be able to do it, but do I have to do it? Why do I need to do it? Why do I need to have this complexity? And maybe this complexity is key to robustness. So that's why we're investigating how we can add different types of neurons into our neural network models and how the performance changes. We are currently investigating the robustness. So by adding noise into the synaptic updates, I didn't present that today. We're still working on those results, but we think that the neural diversity is one of the key factors that could support robustness.
So just to echo, I think the biggest supporter of this view is that Frank Rosenblatt, who came up with the perceptron in his paper in '58. He said the perceptron is first and foremost a brain model. And this is what underlies all of deep learning right now. So all of the ChatGPTs are actually built on a brain model. So this, I think, it motivates us to combine these two together. But the quick question is, one of the biggest issues with deep learning is that backpropagation drives the error learning for the entire network. And that to do this means that you only have one goal. And I think one of the speakers said that for one of the unrobust natures of the networks is that they have one goal and they're brittle to adversarial attacks. So any thoughts about learning rules that we can learn from the brain that might augment this?
Oh, sorry. So I guess there's maybe one learning rule, but it might not necessarily be one objective. Like you could have a neural network trained on multiple objectives in different ways. Like we've done some work with auxiliary objectives, which are commonly used in reinforcement learning, because if you just train a deep neural network to maximize reward, and reward is really sparse, you're throwing away lots of information. So you might just add together lots of terms in your loss that correspond to different objectives and then use backprop to optimize for them. Or maybe like a really popular approach now in deep learning and training large language models would be first train it with self-supervised learning, and then fine tune it with RL or with some other optimization procedures. So mixing and matching objectives, I think, is biologically plausible, is also part of the fold. Whether like backprop as a biologically plausible algorithm, I don't have that much opinion or expertise on, but like the multi-objective part, I think is really cool for understanding the brain, but it's also not foreign to the way that machine learning is working right now, in my estimation.
And if I can follow on that, so I mean, the Brain Initiative is collecting all this data, and we have about all the complexity of what's going on in brains, but also behavior. And so I want to kind of tie into the themes of control here. And both Henry and you talked about generalizing across disturbances and perturbations in new situations. So how do you see this all coming together, and how can the Brain Initiative pull together its resources in the best way to kind of support these ideas going forward? Like, what's the right way of approaching behavior, or these kinds of questions?
Well, I think the most important thing is to get the right behavioral measures, which is actually very challenging. So nowadays you have a lot of good techniques for recording continuous data, but the problem is behavior is too complex. So it's unclear which variable you should track, right? So of course you could track many variables at the same time and have some kind of algorithm to discover what the relevant variable is. So in practice, so we spent 10 years looking at behavior, and it just turns out to be far more complex than we ever expected. So I think we have very good tools for tracking neuroactivity in the brain, and then we know all about the cell types, but behavior is largely a black box. And I think people have vastly underestimated the behavior, even in very, very simple paradigms like Pavlovian conditioning, for example. I don't think anyone understands how Pavlovian conditioning works in terms of the actual behavior that's generated. I think that's going to be the main challenge in the next 5 to 10 years.
And we have, I believe, 5 or 10 seconds left in the session. It seems like I don't see anyone getting up to leave, so maybe we can take one more question from the audience, and if it's a quick one.
Hello. I'll try and make this quick. First of all, thank you for coming here, and I appreciate seeing people in AI and engineering taking neuroscience seriously. My question is, how do we encourage more AI researchers to take neuroscience seriously in an era where attention is all you need? We don't need recurrent networks. The scaling hypothesis will just get us everything we need. We just need more neurons and GPUs. What do you think we should do? Sort of the converse question of, coming from AI.
Yeah, I mean, I guess, the vast majority of engineers in AI will probably not be doing research at the border between neuroscience and AI, and I think that's fine. At this point, I think that AI is a technology that can actually deliver results. Companies need it to perform particular tasks. There are great packages, and you don't really need to be pushing the limits of what's possible in order to deliver actual results, in the same way that, a civil engineer might not, I don't know if this is the best example. Certain engineers don't need to be at the cutting edge of physics in order to push their branches of engineering forward. That said, I have found, I've had some visibility advocating for the border of neuroscience and AI, and I have just seen a tremendous amount of interest by AI scientists who, many of whom do recognize that scale is not all you will need, that there remain challenges going forward. And I think we're really helped by the fact that many of the sort of older generation, the senior people in AI who made a lot of the breakthroughs, including the so-called godfathers of AI, Jan LeCun, Yoshua Bengio, Jeff Hinton, all are very explicit about the degree to which they got inspiration from neuroscience. And I think that has been super helpful. So,
if you have a quick last word.
I've also found that if it really depends on who you're talking to and in what context. If you're talking to an engineer who's working on like Gemini, a really large model at DeepMind, and saying you need to do this like the brain, they're probably going to say we're mostly focused on just scaling it up and getting more data in it right now. That's working really well. If you're talking to somebody who's interested in basic research, though, everyone's genuinely curious how neuroscience works, how the current models compare to what the brain does. They're looking for new ideas. And if you talk to researchers who are looking for new ideas, they're really curious about the brain as a reference point. I think that's really good news for basic research and for like academic and fundamental research, because that's like where a lot of the work at this interface comes from. If you're looking for ideas, there's already a lot of curiosity, and you're not fighting quite as much of an uphill battle as you are if you're saying stop training GPT and make brains instead.
One other thing that I want to point out is what Tony mentioned earlier, which is identifying problems that these brain-inspired computing paradigms are uniquely good at. So like embodied AI seems to be one of those. And of course, another limitation is going to be the hardware, but I'm partial to it. I don't think we can scale up. We're just going to burn everything down, but just by scaling everything up will take up all the energy. So
thank you everyone for coming.